Hi everybody, welcome back to Factoring Quadratic Trinomials. Last time we learned how to factor a quadratic trinomial where a was equal to 1, but today we're going to focus on those trinomials where a is not equal to 1. And I've actually got two methods for doing this, but in this video I'm just going to show you the first method. And the first method is all about making a 3-term polynomial into a 4-term polynomial and then factoring by grouping. Let me explain how it works, okay? So again, we're talking about quadratic trinomials, and anytime we are starting to factor any polynomial, we have to factor out the greatest common factor first if it exists, okay? So do not forget, always factor out the GCF first if it exists. If there's a GCF, it comes out, and then we examine the leftovers to see if it can be factored further. If it turns out that we have a quadratic trinomial where a is not equal to 1, this is the procedure for factoring it. So, like before, we looked for factors of c that add up to b. This time, though, because we have a value for a, what we're going to do is we're going to multiply a and c together, and we're going to find factors of that product that add up to b. Okay, so again, we're going to find a pair of factors for a times c whose sum is b. Once we find that factor pair, we are going to rewrite the middle term, which was bx, as the sum or difference of those two factors from step number 3. So again, we're breaking one term into two separate terms. Once we break it into two terms, we're going to have a 4-term polynomial, and we are going to factor by grouping. And when we're done factoring by grouping, if there was a GCF, we need to remember to include that from step number 1. Now, I know that sounds kind of complicated and kind of long, but let me show you exactly how it works, okay? So let's consider the polynomial 3x squared plus 10x minus 8. First thing we ask ourselves is there a GCF for all three terms here? And the answer to this one is no, there's no GCF. Once we figured that out, what we're going to do is we are going to multiply a and c together. So we're going to take 3 times negative 8, and we get negative 24. All right, so a times c. Now we're going to find factors of negative 24 that add up to 10. Okay, so we're going to think of factors of negative 24 that add up to 10. And if we go through our factors, we realize that the factors that add up to 10 but multiply to be negative 24 are 12 and negative 2. So what do we do with 12 and negative 2? Well, our 10x term from before is going to be broken down into two separate terms. A 12x and a negative 2x. And you'll see that the sum of those two things is actually 10x, which is the original term. So we didn't change the value or anything. We've just rewrote 10x as 12x minus 2x. And those two numbers came from the factor pair that added up to 10. So here we are. We've got our 4-term polynomial at this point. We learned in a previous lesson that when we have a 4-term polynomial, we factor by 2 by 2 grouping. 2 by 2 grouping. So group the first two, group the last two, find the GCF of each of the terms, and put the GCFs together as one factor, and then, the GCF is what they have in common, right? So x plus 4 is the GCF. That's one factor, and then the leftovers are another factor, okay? So you can see it's not terribly difficult. It's just this first new part where you have to find factors of AC that add up to B. Let's try this one, okay? So we're going to factor first, and remember, the first thing we're going to do is find a GCF, and this polynomial function does have a GCF, and if we think about what it is real closely, it's going to be, what do you think? 2x squared. So 2x squared is our GCF. And when we factor the GCF from all 3 of the terms, we get 3x squared minus 58x minus 40. All right, so the GCF has come out, okay? At this point, we're looking at the quadratic trinomial in the parentheses, and we're going to go through our factoring procedure to see if it can be factored. So do you remember how that works, right? A times C. So 3 times negative 40 is negative 120. What we need to do is figure out, is there a factor pair of negative 120 that adds up to negative 58? Why don't you pause the video a second and see if you can find the factor pair. Okay, so you found the factor pair. It should be negative 60 and 2, right? Negative 60 and 2. So what we're going to do is we are going to rewrite this trinomial, but we're going to split up this middle term into two separate terms, okay? So this now becomes, don't forget about your GCF hanging out there, 3x squared minus 60x plus 2x minus 40. So I'm going to go ahead and do 2 by 2 grouping at this point. And we've got 2x squared, and then the GCF from this group is 3x. And when we factor 3x out, we get x minus 20. And then from this group, the GCF is 2. So we factor a 2 out, we get x minus 20. And guess what? Hey, look at that. X minus 20 is in common, and we know we did the right thing. So 2x squared is the first factor. The GCF is actually x minus 20 of the whole polynomial, and then the leftovers, 3x plus 2, is the third set of parentheses. Okay, so the second part of this question says, since this is a function, use the zero product property to solve this function for its zeros, okay? So the zero product property, remember, means that our function is equal to 0. And if we're multiplying things together and the product is 0, then each of those things could be 0. So we're going to take each of those factors, 2x squared equals 0, x minus 20 equals 0, and 3x plus 2 equals 0. And we're going to go ahead and solve. We're going to solve for x. So in the first one, we divide by 2, and then we take the square root, and we get x equals 0. In the second one, we add 20 to both sides, and we get x equals 20. And then in the third one, we subtract 2, and then divide by 3, and it turns out that x is equal to negative 2/3. So what I want you to do now, that we've solved this algebraically for its zeros, I want you to go to Desmos, and I want you to type in this function, and I want you to graphically find the zeros. And what you should hopefully see is that the zeros of this function match up with what we found algebraically. Now I know it says use GeoGebra, but we're actually going to use Desmos to do that. Okay? All right. To continue on at this point, we're going to talk a little bit more about functions and polynomial functions and just different variations of the way that we might see the same exact procedure. So like this, for example, if we have the function f of x equals 3x squared minus 4x, and we want to find all the values for which, values of a for which f of a is equal to 4, then what is it saying? It's saying, okay, in function f, if a is the input, the output is 4. So a becomes my input instead of x, and the output is equal to 4. So all the x's become a's, and my function is equal to 4. So this is what we got, right? And we learned earlier that there are two ways to solve this type of equation. We could first use the zero product property, or we can solve it graphically. We're applying the zero product property here, so what we need to do is make sure that it's equal to 0 first. Okay, so notice what happened here. We subtracted 4 from both sides, and we made it equal to 0. And then we went through our factoring process. Okay, so factor, and then here's my zero product property. I'm going to call that the ZPP for short. And it turns out that my solutions are a equals negative 2/3 and a equals 2. Now, a few units ago, we learned how to find the domain of a function. And the functions that we found domains with before had a linear denominator. So these are rational functions, right? So these are functions that are in the form of fractions, like the one shown below. And remember how we found what are called the restrictions on the domain. On the restrictions on the domain, we said the denominator cannot be equal to 0. So if we can figure out what values of x make the denominator equal to 0, then we know that those are restrictions on the domain. Well, a couple units ago, we just did linear denominators. It made it easy for us to find the restrictions. But now that we have these techniques of factoring and the zero product property, our denominators no longer have to be linear. For example, in this function f of x, our denominator is quadratic, right? So if we can figure out what values of x make the denominator equal to 0, then we can find the restrictions on the domain. So what do? Well, we take the denominator and we set it not equal to 0. And then we factor. We factor to see what values of x cannot be in order to make the denominator equal to 0. So we factor, use the zero product property, and it turns out in this function that x cannot be equal to 3 and x cannot be equal to -5. Now, these are our restrictions on our domain. Okay, this isn't the domain yet. These are the restrictions on the domain. So how do we write the domain with those restrictions? Well, remember, we can write it in set builder, or we can write it in interval notation. And this is what they look like when we acknowledge that there are restrictions on the domain. All right, so that takes care of our lesson for the day. Remember, it's about factoring quadratic trinomials where a is not equal to 1 using the zero product property, and finding the domain of functions now that the rational function denominator is not a linear polynomial. So if you have any questions about this, please contact me. Otherwise, why don't you go ahead and try practicing this. Head back to our Schoology page, read the description of what the practice is, check your answers, and let me know how it goes.